Now that we've discussed security at basic levels and explored the details of the Android operating system and some of the security features of that particular mobile platform, let's go back and review the security features and how they differ from the other platforms. This module addresses iOS security. We want to understand the architecture of the iOS operating system and its security model. It's important when we compare the various phones or mobile platforms to understand that manufacturers perhaps have differing incentives and make decisions on the design and architecture of their systems based on those incentives. Consider the business model of Android compared with Apple and iOS. Google builds the Android operating system and puts it in the public domain. It gives it away. Phone manufacturers license Android but don't pay for it. So their method, their incentive to adopt the Android operating system is widespread use and low cost. Ask yourself, how does Google make money by giving away a mobile operating system? And remember that Google makes money by collecting statistics on users' use patterns, summarizing those statistics, and selling them. They also sell advertising. Apple, on the other hand, manufactures the iOS operating system and tightly controls the manufacture of the iPhones and iPads that it runs on. Apple makes money by selling hardware. Apple's other revenue stream comes from a different source. Consider how an iPhone or an iPad is managed by the user through the iTunes program. iTunes is a music management platform. Why would you design a system that managed a mobile computer like an iPad or a mobile phone with a music management system? Examine the incentives and you realize Apple makes money by selling music and videos through its iTunes system for installation and play on the mobile platforms. Some other decisions are influenced by these types of incentives. It's important to remember them. The iPhone or iOS architecture is similar to the Android architecture in that it's a layered operating system. It's based on a Unix, just as Android is, but with a different user interface and slightly different internal architecture. This slide is much less complex and much more simple. Some even might say the colors are more visually appealing. In general, it's consistent with the Apple and iPhone experience. Like Android, but designed in Cupertino, as we say. At the low level, we have physical storage, a digital key embedded in the hardware. In the current version of the iPhone 6, we have an embedded secure element and a near-field communication system. The file system on the iPhone is by default encrypted. Storage is segregated into a system partition where the application files are stored and a user partition where data and applications go. The life cycle of an application on the iPhone is simple. The application starts, it's initialized. While in use, it may go in the background. Remember the side channel data leakage threat we described earlier, where the screen is snapshotted and as the application comes back, that screenshot is displayed. The application developer is responsible for ensuring that that screenshot is cleared, that it doesn't unintentionally leak sensitive data or leave it stored in an unsecured portion of the phone. At the end, when the program terminates, the application developer is responsible for cleaning up the memory and managing it. The applications for the iPhone are written in Objective-C and, starting with iOS 8, Swift. Objective-C is a C family language, which means it shares all of the obligations on the programmer to allocate and manage memory securely. Java, as a higher level, more modern language, takes care of all of those things for the programmer and developer. as does the C# language used in the Windows platform. On the iOS platform and the BlackBerry platform, which use a C family language, it's incumbent upon the developer to use safe and secure coding properties, coding methods, and functions to manage memory appropriately. Bugs that can occur because of memory management issues include buffer overflows, as discussed previously, and other specific problems, integer overflows, double freeze, format string bugs, etc. Review the OWASP Top 10 for iOS specific vulnerabilities, and review the CVE for iOS specific vulnerabilities and avoid these problems. Learn from others' failures. In addition to address space layout randomization present on the Android and other platforms, iOS includes data execution prevention. Data loaded into memory is loaded into an executable space or a data space. So if code is loaded into the data space by an attacker, it is prevented from executing by data execution prevention. In general, don't allocate memory until the user has authenticated. Provide careful care of keys and references to keys, and utilize the randomized memory. Storage on the iPhone is a little different. There is no removable SD card, so no removable storage. We avoid that problem. Memory is encrypted on the iPhone, and files or data is stored in files andplists or preference lists. Additionally, there is a SQLite database, as is present on the Android, and a specific construct called the keychain for management of login and password information, also known as credentials. Off the device, the iOS is tightly integrated with the iCloud and other networking features. What's involved in getting an application into the store? Well, with the iPhone, you can expect more scrutiny than you did with the Android platform. Apple will issue a developer a digital certificate and requires that iOS applications be signed with that Apple-issued digital certificate. It's reasonable to assume that they will perform some dynamic and possibly static analysis on the source code submitted, and then a human being will actually test the usability and functionality of the application and the user experience. It is possible, as with Android, to decompile iOS applications, but it is not as easy to get to readable source code as it is with Android. Nonetheless, a security professional should assume that this process will take place and should use obfuscation techniques as you would in the Android platform. iOS code must be signed. The code signature is verified upon loading of the application to the iOS store or the iTunes store, and upon runtime when the application is downloaded and installed in the phone and when executed. This code must be signed with an Apple-issued certificate, the public key for which is stored in the iPhone at manufacturer. So when an application is loaded or installed and when it's executed, that digital signature is validated by the iOS. The keychain provides protected storage for credentials, login and password pairs. Here's how it works. When a user tries to log into an application, in this example, an FTP remote server, the keychain will intervene and check to see if it has a previously stored login password pair. If it does, it will supply the login and password to the remote application. If the application login password is successful, the control is returned to the user. If there is not a previously stored login password, or if that login and password attempt is not successful, the keychain will prompt the user for their login and password, and then again attempt to authenticate to the remote service. If that's successful, the keychain will prompt the user asking for permission to store the login and password, store it, and return control to the user. The advantage to using the keychain is the user can use unique, long, and complex passwords for each different website or remote service he uses. SSL and TLS are supported on the iOS platform, and additionally DTLS or Datagram TLS for datagram services. This works exactly the same way as with Android. We recommend you use SSL version 3 or TLS version 1.3 or better. Remember, when implementing applications for mobile phones, you as the developer or security professional are responsible for implementing the SSL correctly, validating certificates, and handling errors. The browser isn't there to handle it for you anymore. iOS also has a concept of a sandbox. Works almost exactly the same as with the iOS platform. However, there are less limitations, fewer fine-grained access controls as provided by the Android manifest.xml file on the Android platform. Thank you.